So welcome to lecture 6 of electrical machines course. So we are continuing with principles of electromechanical energy conversion. Last class also we discussed about electromechanical energy conversion where we derived the expressions in different ways for magnetic force, right? Sometime in the uniform magnetic field using the inductance, and also like we have also derived the general expressions for magnetic force. And also we discussed the losses in the magnetic material like hysteresis loss and eddy current loss. Okay. So today also we'll continue this electromechanical energy conversion. And last class we are doing one problem in fact. So we'll continue with that. So the problem is this. This is the magnetic circuit. The figure is given here. Actually, that is 3.7 in the book. So it is excited by 100-ton coil, right? N is 100 here. And the coil is wound over the central leg here. So determine the current in the coil that is necessary to keep the movable part suspended at a distance of 1 centimeter. So this is your movable part, this iron bar, right? This is your movable part. And the question is, we need to find the current in this coil that will give a attraction force to this iron bar and which will remain suspended at the length of 1 centimeter, right? So this length should be 1 centimeter. That is taken here x, right? So that will remain suspended at 1 centimeter. And what is the energy stored in the system, right? So energy stored in the system, already we know, right? So in an inductive system. And this you can see here, this already it is mentioned that this is the permeability is constant, right? Here the relative permeability and the density of the magnetic material are given. This is your relative permeability of the material, 2000, and 7.85 gram per centimeter cube is your density of the material, right? So this density, in fact, it is required to calculate the mass of the this iron bar. We'll see how it is, right? So now, because the permeability is, we are assuming it is remaining constant, the relative permeability is at 2000. So therefore, we can use the inductance approach to find the force here. So if we know the inductance of any circuit, magnetic circuit, we can find the force also. Already we have calculated it, right? And that formula already you know, that is the magnetic force is nothing but it is equal to half of I square delta L by delta X, right? Already we know this. And somehow or other, if we can express this inductance L in terms of X, X is this, right? Then I can find the Fm, right? The force. So easily in terms of X by taking derivative of inductance. And then after finding this force because of this coil, I can easily equate this force with the gravitational force that is being applied on this iron bar, right? So the gravitational force, obviously it is equal to mg, right? If I'll write gravitational force, that is equal to mg, mass into gravitational constant, right? So after finding this both forces, so in order to make this iron bar in equilibrium position, that means in the suspended position at 1 centimeter, so I can equate this force, magnetic force, with the gravitational force. So that will, after equating, I can find, in fact, the what is necessary? We need the current, right? Current I can find, right? Because L is a function of current, obviously. So I can, here current is there, I square. So I can show you how to proceed. You can see here. First, we need to find the reluctance, because in order to find the inductance, we need to find the reluctance of this circuit. So how we'll find the reluctance? So there is air gap. There are 3 air gaps you can see here, right? And we have, these are the magnetic material paths, or you can say iron, right? Ferromagnetic material. And these are also will exert some reluctance, right? So we have now 3 components of reluctance. One is your air gap here, 3 air gaps, and one central limb, right? And other one is your outer limb. Outer limb is this, right? So up to this we can consider as outer limb. Up to this is your outer limb, and this is your central limb, right? And these air gaps, obviously. So now if I'll plot the equivalent circuit for this magnetic circuit. How I can plot? So this is your source, right? So I can use MMF here. So that is F, that is represented as F, right? So that is nothing but equal to Ni. Okay. So MMF is here, and your central limb, the reluctance, let us say RC. Okay. And we have 3 air gaps, those are connected with the outer limbs, right? Outer limbs as well as central limb. So now I can put the air gap reluctances here. So one air gap reluctance in series with the one outer limb reluctance, and other one is with other outer limb reluctance, and the third one is with in series with RC, right? So now this is your equivalent circuit. Now from this equivalent circuit, can we find the net reluctance so that we can find the inductance of this whole circuit, whole magnetic circuit? So now the equivalent reluctance we can see here. These are in series, so I can add it together. And these two are in parallel. This one and this one, they are in parallel. So I can use the parallel addition theorem, right? Just add, we know how parallel resistances can be added. And then it can be connected in series. It is connected in series with RG and RC here, right? So now finding the equivalent reluctance. So this will give me RC plus RG. That means this RC plus RG plus, because these are equal. So therefore, with the parallels, for the parallel circuit, it will be half, right? The equivalent reluctance will be half. So therefore, 0.5 into RO plus RG. Okay. So now the whole reluctance. So the reluctance already we have seen here. The RG is given in terms of X, right? Here. So therefore, your reluctance will become a function of X. We can see here 5.272 into 10 to the power 5 plus 11.937 plus 10 to the power 9x. Okay, so x is that distance between, that is the air gap distance, right? So now I can find L. That inductance is nothing but, we know, n square by r, that is n square by reluctance. So by that way I'll find 1 by 52.72. So already it will cancel out. So then I can use this formula of magnetic force. Already I told you. So magnetic force is nothing but half of I square delta L upon delta X. So now using this formula, I can write Fm will be equal to 5.9. So just take the derivative of this and of L, right, and multiply with I square. Okay, so this will give me this equation, right? 596,850 by, so minus sign will come because we are taking derivative of a fraction, so minus sign will come. So now your Fm will become, if I will put x equal to 1 centimeter, because my air gap should be 1 centimeter. That means the question is here, it is asked that this iron bar will remain suspended at 1 centimeter. That means your x will become 1 centimeter, right? So now substituting x equal to 1 centimeter in this equation, my magnetic force will become this, right? 4.15 into 10 to the power minus 3 I square, that is Newton. Okay, now this magnetic force is to be equated with your the gravitational force and the iron bar. So at x equal to 1, this value is this. So now if I'll calculate the gravitational force Fg, that is nothing but equal to mg. So I can substitute m is the mass. So mass I can find density into volume. So density is given here and volume is 11 into 1, right? So that will 11 is the square cross sectional area, right? And into 9.81. So that will give me around, so a 0.847 Newton. So now if I'll equate this both Fm and Fg, now I can find the value of current, that will be 14.28 ampere. So that means I need a current of 14.2 ampere to flow in that coil, so that your iron bar will remain suspended at 1 centimeter position. Okay, so this is, I think this is fine with you. You all understood this concept, right? Now the question is the stored energy. So we know in the stored energy in an inductive circuit we find half Li square, and that is equal to 0.5, 83.4, just by substituting the values. Okay, respective values, I found 8.5 millijoule. Okay, so now your problem is solved. We found the current which is required to suspend the iron bar at 1 centimeter distance, and the energy stored in the coil, in the magnetic circuit, right? So this is 8.5 millijoule. Okay, so now this is up to your magnetic force and some development of magnetic force, right? So now we'll come to the real fact of the electrical machinery, that is when a uniform magnetic field, there may be two options we have. One is if we have a uniform magnetic field and a coil is there, what will happen? And suppose the magnetic field is varying, then if we'll put a coil, then what will happen? A coil means a coil with some current or with some force, right? So first we'll consider a coil in a uniform magnetic field. Uniform magnetic field means your magnetic field is constant. That means if I have a magnet with north pole and south pole, so the magnetic field of the lines, these flux lines, will be uniform throughout, right? So that means your it is constant. Okay, it is not varying with time. Okay, so another case we'll consider where magnetic field is varying with time. Okay, so now we'll consider just uniform magnetic field. That means your magnetic field is constant here. Okay, now if the magnetic field is constant and I put a coil here, right? A simple coil I put here, then what will happen when the coil is being injected with some current, and or else if the coil is being rotated inside the magnetic field, that means I give a force in the coil and the coil is rotating. So under that condition, what will happen to this in this magnetic field? So already we know that when inside a magnetic field a current carrying conductor will be there, then the force will be developed and the current carrying conductor, right? And also when a force will be given to the to the coil. So an EMF will be developed across these terminals, right? So we'll see how it is. Let us discuss this in detail. So now we can see this is very special to rotating electrical machine. So a rotating machine has two essential parts. Now one is a stationary part, right? So we call it stator. And there is a rotating part which we call the rotor. That means if your magnetic field is developed by the stator, we'll put the coils on the rotor, right? So then the operation will happen and it will act as a motor or generator. Or else if we can put the magnetic field or magnets on the rotor and we'll put the coil on the stator, that will also work, right? So therefore there is a stationary part. We don't know in which part which thing is there, whether the coils are in the stator or there are different structures for different machines, right? Okay. So now the rotor of a DC machine is usually referred to as an armature. Okay. Why it is called armature, we'll talk about it in near future in this class also. So the outer diameter of the rotor is smaller than the inner diameter of the stator because the rotor have to be accommodated inside the stator, right? So therefore the outer diameter of the rotor must be smaller than the inner diameter of the stator so that it can rotate freely inside the stator. Okay. And therefore a rotating machine is a device with one continuous and uniform air gap. That means one air gap is there, very small air gap, and it is continuous and uniform. So you can see in your machine lab when you will come here to institute, I think in your machine lab it will be shown. So how the machine structure is, and the air gap was kept very minimal, very small, right? So both the stator and the rotor are made from highly permeable magnetic materials so that the reluctance of each is negligible compared to the reluctance of the air gap. So that means the permeability will be very high for those materials used for making stator and rotor. Okay. Hence, almost all the MMF in the magnetic circuit of a rotating machine is consumed to establish the required flux in the air gap. So the constant magnetic field can be set up by either an electromagnet or a permanent magnet. So both can be utilized, not simultaneously, but either you have to use electromagnet or permanent magnet. So electromagnet means it is excited externally by some source, by some current source. And a permanent magnet means it is already a magnet and it is being used, right? Already it achieved its saturation and it is a magnet. So an electromagnet is formed by winding a coil around a magnetic material. A machine with electromagnets is called the wound machine. So the machines, those use the electromagnets, they're called wound rotor machines or wound machines especially, right? A machine is said to be permanent magnet machine when the field is set up by permanent magnets, right? They're called permanent magnet machines. So the advantage of a wound machine is that we can control the flux in the machine by controlling the current in the coil. This is the advantage of wound machine. You will find in our lab almost all machines are wound machines. So where you have to give external excitation and also you can control the excitation by injecting or by controlling the current in the coil, right? So the permanent magnet machine has the advantages of its small size and its efficiency is higher than that of wound machine of the same power rating because in order to manufacture a electromagnet we need different slots, we have to put the coils, right? So therefore the size becomes larger as compared to permanent magnet masons. And also the efficiency is higher in case of permanent magnet masons because there is no loss in the coil which is acting as electromagnet, right? Because when we put some wear around some coil, so that wear itself has some losses, right? So that happens in case of electromagnets, not in the permanent magnet. And therefore the efficiency of the permanent magnet mason becomes higher as compared to the owned masons, right? So now let us consider the generator action in this discussion where we are considering a coil in the uniform magnetic field, right? So the generator action means how, what is the generator action? The generator action indicates that when the coil is inside the magnetic field and we give a force, we apply force on the coil, that will produce, because of the change in the flux linkage to the coil, that will produce an EMF in the coil, right? So that we have to see here. Here let us see, this is a typical structure of a electrical rotating mason, where you can see this is your yoke. Yoke means it is complete outside. That means your frame, right? Where the mason is being accommodated. This is your yoke around. So inside which the mason is accommodated, right? We call it yoke, okay? And then after, also we call it starter. And here is your rotor, right? Inside it, and this is your air gap. You can see this is your air gap. This path is your air gap, right? So now we can see here that inside the yoke we have certain, one is a black color, one is a white color. This is your north pole and this is south pole, right? That means this is a magnet with north pole and south pole, right? And we have a rotor where we put one coil, right? The coil is having two terminals A and B, or we can say two conductors A and B. Okay, because here it is a cross section, we only see the cross section of the conductors, cross section of the rotor, cross section of the starter. So here we are seeing the cross section of the conductor, where these are the two sides of the conductor, right? Two sides of the coil. Suppose your coil is like this, okay? So your coil is like this, okay? And now these are the sides of the conductors. One is A, other one is B. And if we'll take the cross section, it will look like this, right? One is here, one is here. Now, if this rotor is rotated in this direction, that means in clockwise direction, we can see here clockwise direction, right? So if it is rotated in the clockwise direction, now what will happen in this coil? Okay, so this is your rotor. You can see the actual rotor here. And this is your conductor. In fact, you can see here, this is your conductor, right? And it's not visible clearly. So this is your coil, okay? And this is your conductor A, this is your conductor B, okay? So now your magnetic field, if we'll see, it is, you can see here, this is the magnetic flux is being generated, right? And here also you can see the magnetic field, right? It is downward, okay, from north pole to south pole. And now the torque is being applied on this rotor, or you can see the force is applied and this rotor, and the rotor starts rotating. So initially it is in the flat position, we can see here. And under this condition, the flux linkage is maximum, because we can see all the flux is passing through this coil, right? That means maximum flux linkage is under this condition, okay? Maximum flux linkage. Okay, now if I'll rotate it slightly, then what will happen? Suppose I rotated it, A will come here and B will come here, right? So then what will happen? Your flux linkage will reduce, right? Because some of the flux line will not be enclosed inside this coil, right? We can see here. So that means your flux linkage will reduce gradually, right? That means there is a change in flux, but reduction of flux linkage, right? So reduction of flux linkage to the coil. So then what will happen in that case? So as per the Faraday's law, so there just see the rotations, how it is being rotated. We can see here, right? Rotation is being take place. So now your conductor A came here and conductor B came here, right? So this is now, you can see it here, right? Okay. So this is now the conductor A, conductor B, it is slightly rotated and the flux linkage is reduced. Now what the Faraday's law says, it says the EMF induced will be the rate of change of flux linkage to the coil, and in fact the it opposes the cause, right? So that means the cause here is the change in flux is in the reduction way, right? So the flux linkage is being reduced. Now the EMF will be produced in this coil in such a way it will it will inject a current in the coil so that in such a direction so that it will try to enhance the flux linkage, because your flux linkage is reducing, right? Because when we're moving it clockwise direction, your flux linkage is reducing. So now the EMF will be produced in such a way that the current will flow in this coil. That means if we'll put an external resistance here, right? So obviously, so the EMF will produce in such a way, the current will flow in such a way that it will oppose the cause, right? So here the cause is reduction of the flux linkage. So therefore, it will help the flux to increase, right? Inside the coil, right? How it will happen? So you can see if it is your so now you can guess in what direction the current will flow so that your flux linkage will be strengthened more and more. So if I'll put the current direction in this way, right, in this direction, then by by the circuital law, if we'll see, right, so your flux linkage will be which direction? Your flux path will be because of this current. So what will happen? Your flux linkage will reduce or it will increase. It will in fact, right? So in fact it will reduce, right? Okay. So if we'll see, because your flux direction produced by this coil will be like this, and it will oppose the main flux because of this field, right? So when it will oppose, that means it will reduce more and more. Therefore, your current should flow in this direction. That means, sorry. That means from A to B. That means from A to B it should flow, right? So if it will flow from A to B, then the main flux in this coil will strengthen. That means it will increase, right? That means it is opposing the reduction of the flux linkage, right? So that means your current need to flow from A to B. So therefore, if I'll put one resistance here across these terminals, then obviously the current will flow like this, right? So that means your positive terminal will be B with respect to A. So your terminal A will become positive and terminal B will become negative, right? So now move to next rotation part. So now your coil has moved 90 degree up to 90 degree, right? So here is your coil, right? Okay. So now if we'll see, if it is rotated here in this fashion, suppose it moved to here at this point. So this is your A, this is your B, Now, what is the flux linkage? If we'll say the flux linkage is 0, flux linkage in the coil is 0, right? So that means when the coil is in the 90-degree position, the flux linkage is 0 completely, right? Again, when it will rotate to this position, suppose it became to this position, right? This will be A and B. Now from 0 to, again the flux linkage will increase, right? So flux linkage will increase means your current direction should be in opposite direction, right? So your current direction opposite means we can see here in here, right? Okay. So now your current direction will become opposite, right? So this way, if we'll just go through, and finally when it will come again to position B, the flux linkage will again maximum in the negative direction, right? Okay. So in this way, if we'll proceed, so now we can see the representation of the volt flux and flux linkage and the EMF induced, right? We can see here, this is your yoke, this is your north pole and south pole. If we'll made it flatten your the magnetic path, right? So this is your north pole. We'll cut the machine and flat it. It will look like this. Your yoke will look like this. Your magnets attached to the yoke will look like this. This will be your north pole. This will be your south pole, right? Now the flux produced by this north pole and south pole, they will look like this, because north pole, from north pole it is going to south pole. Therefore I'll represent the flux produced in the north pole as positive, right? So, and in the south pole it is negative, right? Let us say it is 5p is the flux, which is constant and uniform throughout, right? So this is the flux produced by the magnetic electromagnet or magnet, whatever. Flux produced by the magnet. Okay. Now, if we'll see the flux linkage to the coil, what is happening? So when at 0 degree, okay, when the coil is in the flat position, already we have seen, at that time the flux linkage is maximum. That means your flux linkage is 5p, right? At this point, that is maximum flux. And gradually when the coil will move with some angle, right, it will gradually decrease, right? And again when it will achieve 90-degree point, the flux linkage will become 0, almost 0, right? And then again when it will start rotating towards 180-degree, then flux linkage will increase, but in the negative direction, right? Okay. So it will go in the negative direction, and again at the location of pi, it will become highest, but in the opposite direction, right? Okay. So now it will go on, as we rotate the coil, the cycle will repeat, right? So this is the flux linkage by the coil. Okay. So flux linkage to coil is this. Now if we'll write the function for this flux linkage, I can write it as phi equal to phi p cos theta, right? If I'll say the theta is the angle of rotation, then I can write it as phi p cos theta. Okay. Now if I will find the induced EMF in the coil, so it will be minus d phi by dt. So that will be negative sign of d phi by dt. So if I'll take the derivative of this, it will become phi p sine theta d theta by dt. And we know d theta by dt is nothing but this is equal to omega, right? So omega is equal to d theta by dt. That is the angular speed of the rotor. Okay, so I can write it as phi p omega sine omega t. Okay, so now your induced EMF in the coil or across the coil is nothing but it is phi p omega sine omega t, right? So now we can see here how we'll collect this voltage because the coil is rotating inside the machine, right? How we'll collect it. So therefore, two slip ring arrangements are there. We can see here the slip rings are fixed to the rotor. Okay, through some insulating material. It is so here there are insulators inside part, right? And it is fixed to the rotor, and the outer part of the slip ring is connected by the ends of the coils. So end A is connected to this, you can see here, right? And end B is connected to this, right? Now the slip ring is fixed to the rotor, and both the ends of the coil is connected to the connected to the slip ring. Now the question is how to collect the voltage. So if we'll put here the brass, which is pressed by the spring, right? And the brass is fixed outside and it is pressed, and the brass will move when the rotor will rotate. The brass will move on the slip ring. Okay, when this brass will move, as it will rotate, the brass will just move on the slip ring, and it will remain in contact with the slip ring, and by that way, so this is a carbon brass and it is good conductor of electricity, so therefore we can collect the voltage across this. So this will be your positive and this will be negative in one cycle, and then it will change, right? As it will go on rotating, the cycle will change, right? So this is how we collect the EMF at the terminal of the generator. Now the question is this kind of arrangement, suppose we reverse the constructional feature. Suppose the magnets I put in the rotor, so north pole and south pole in the rotor. So this is your north pole and south pole, it is a rotor, and on the starter itself I put two coils, right? And if I rotate this magnet inside, right, this is your starter, let us, okay, this is your air gap. Now if I'll rotate this rotor with north and south pole, this will also produce the same thing in the starter, right? Then why to go for this arrangement with slip ring? So therefore this kind of arrangement is mostly used in the synchronous generators, right? Where we produce alternating current, right? We call it sometime alternator, right? Also we call it alternators. So it produces alternating current and voltage. so therefore this kind of arrangement, that means the magnet or the electromagnet is put on the rotor and the armature winding is on the starter. And in case of DC machine, in fact, we put the armature winding on the rotor and the field or the magnetic field on the starter, like we are analyzing here. But in fact, when you are doing this kind of analysis, it is producing AC, right? Alternating current. But how will convert it to DC? This is a question, right? Now how I will convert this to DC current or DC EMF, right? So just by doing some simple arrangement, I can make it DC, because you can see here, if we can arrange two commutator segments, or we call it split ring, right? This is also called commutators. Or commutator segment, or sometimes it is called as split rings, right? Split ring means the same ring splitted and there is no connection in between. Now with the split ring, one end is connected to one split and other end is connected to other split, right? Because there is one coil, so we have two split, only we are splitting once, right? So if there are many coils, then we have to split many times, right? So this is called split ring with dividers, insulating dividers, right? So these are the insulating dividers. So these are called commutator segments. And when the brass moves on this commutator segment, in fact, right, when this moves, this commutator segment, you will get DC current here, because your positive sign will never change, because whenever the coil will rotate and come to this side, it will again become, suppose here conductor A is giving under north pole it is giving plus, and the under south pole coil conductor B is giving minus. Again when it will rotate and conductor B will go to north pole, it will become positive again, and conductor A will become negative again, right? So that means your commutator segment here, the EMF induced remains constant, right? So here it will be positive, right? Here it is negative. So it will remain always constant on the commutator segment, and therefore through the brush we can uh, extract this EMF, right? Okay, as this commutator will move, this will be positive in first half cycle. Again when it will move, again it will become positive in the next half cycle, right? So one important aspect I forgot to tell you here, we can see here that when the rotor is moving half a cycle, right? We can see here, and your EMF is also half cycle, right? Okay, that means when your rotor is moving half cycle up to pi, sorry, your EMF is also pi, right? And when again it is completing 360 degree, your EMF is also completing 360 degree. That means what it indicates here. So if I'll measure the angle here in the EMF, let us say theta, that we call electrical angle. So please remember, this is very important for electrical machines course. This we call electrical angle. When the angle is measured in the induced EMF, right? And when we measure the angle in the machine itself, right? So we call it mechanical angle. That we represent through theta m. Mechanical angle. So in this case we can see that theta m is equal to theta, right? That means mechanical angle is becoming equal to electrical angle. That means how much I am rotating in the mechanical space, right? So that is also being reflected in the electrical angle in terms of EMF cycles, right? So now suppose if I'll change the number of poles, it will affect, right? I will see in the next slides, right? So this is how here we can find the voltages at the terminal. Here we can see, right? If we'll see the positive cycle for the first cycle, it will be this, and again in the next cycle it will be like this. So it will like exactly work like a rectifier circuit, right? So then we'll get EMI by EM, the maximum value will be EM by R here. So it is the current, sorry, it is the current will be the maximum value of current will be EM by R. But if we'll see the voltage also will look like this with a magnitude of EM, right? Now, so obviously you can find the average value of this, right? You can find the average value and you can go ahead. So now we'll take 4-pole machine. So till now we have discussed 2-pole machine, and now we'll consider a 4-pole machine. You can see here, this is a 4-pole machine. Here it is north pole, south pole, again north pole and south pole, right? And if you'll see the flux path, obviously the flux will start from north pole, it will enter into the south, and it will make a path, right? So every pair of the pole, they will make the flux path, right? Now we have 2 coils. Again, we are considering 2 coils. So whenever we put the coil, that means the coil span, we call it coil span. Coil span means the angular difference between 2 sides of a coil. So angular difference between 2 sides of coil, that is A and B, should not be greater than 180 degree in any condition. If it will be greater than 180 degree, then we cannot get an EMF. So it should not be greater than 180 degree electrical. Electrical, not mechanical, right? So that means when we'll put the coil span, it should be in the range, it should be maximum of one of the magnet, right? That means if we'll span it, That means it should lie from one end of the North Pole to the other end of the North Pole, right? Okay. So because it is a 4-pole, mechanical angle is 90 degree. We can see here it is 90 degree mechanical, right? But electrical angle will be 180 degree. Why it is, we'll see by analyzing the induced EMF, right? We can see here. So now actually your this is also sometimes called coil pitch, right? Coil span or coil pitch, and it should be theoretically always equal to 180 degree. But in practice, we don't get this because we put some slots here. In order to here, we put some slots to put the conductors, right? Therefore, in practice, we are unable to get exactly 180 degree. It is always less than 180 degree, right? This coil span or coil pitch, always it is less than 180 degree. Okay. So now we can see this when this kind of arrangement is there, I can, if I'll rotate this rotor and the coil will rotate simultaneously, then what will happen under that condition? How the EMF will look like, right? So we'll see it. So under this condition, when this is the condition, right? Under this condition, the flux linkage is, we can say the flux linkage is maximum, right? Here we can see the flux linkage here, right? It is maximum. As we move forward, then the flux linkage will reduce gradually, right? In some side it will reduce. Here it will reduce because it will move towards, suppose it will move gradually, it will reduce, right? So as we have seen in the two pole machine also, right? So now gradually if we'll see the flux produced in the magnets and the flux linkage and the induced EMF, they will look like this. So if we'll see here the 4-pole machine, right? We have 4 poles, 2 pair of poles, right? And the flux produced by the poles are like this. The north pole it is positive, at south pole it is negative, look like this. And again, if we'll plot the flux linkage with the coil, so it is maximum at the position when it is 0 degree, right? And then it will gradually move. It will become, sometime it will become 0 when it is at pi by 2. And again it will become maximum negative, right, at pi, right? And we can see here that up to this point at pi, right, electrically pi. So that means it is electrical angle pi, right? So if you'll see the mechanical angle here, so the mechanical pi, so it will move up to this, right? Up to this point means it is mechanically 90 degree. Moving, the mechanical movement is 90 degree, right? That means mechanical angle of rotation is 90 degree. But by that time, when this A will come here, when this A, it will become A and B will come to this position, right? Suppose B will come to this position. Then under this condition, your EMF will become maximum of negative. That means it crossed 180 degree, right? By the time it moved 90 degree, right? So your EMF is producing, going to travel 180 degree, right? We can see here in this figure, right? So therefore, we can see your EMF will become here pi, right? Okay, and your flux linkage will become here negative of maximum, right? So that means for your 4-pole machine, what is happening? Your theta electrical is becoming equal to P by 2 theta m, right? That means the number of pair of poles into the mechanical angle it is traveling. So when your rotor is traveling, suppose theta m, then your electrical angle will become P by 2 of theta m, right? From this analysis, right? So you can see here phi phi p cos theta, and this theta is electrical. In electrical, this is electrical angle. Okay, and this is also electrical angle. Now your induced EMF will become, similarly if we'll calculate, it will become phi p sine theta d theta by dt, and obviously you will become phi p omega sine omega t, right? Now again, if we'll consider a 6-pole machine, so this is for your 4-pole machine, right? 4-pole machine. Now if we'll consider a 6-pole machine here, so then what will happen again? Again, your we can plot the same kind of plots, but your electrical angle will be thrice of mechanical angle, 6 by 2, right? Number of poles by 2, so thrice of a mechanical angle. We can see here, right? So this is your north pole, south pole, north pole, south pole, right? Now we can see that this is your flux produced by the magnet. This is your flux linkage with the coil, right? These two coils, A and B, two sides, right, of the coil, A and B, and this is your EMF induced, right? So therefore, we can conclude that your electrical angle is P by 2 theta m, right? So this is how all the expressions will be same for both any kind of machine. It will remain same, the expressions. Now your theta is equal to P by 2 theta m, and similarly if I'll take the derivative of this, it will become omega, that is speed of the that is the electrical angular speed, and in the right side it will become P by 2 omega m. This omega m is the rotation of the rotor, right? Angular speed of the rotor in mechanical radian per second. And similarly, if we'll find the frequency from this just by converting omega into 2 pi f and dividing 2 pi, I'll find f equal to P by 4 pi omega m, right? Now we know omega m is nothing but, in terms of this nm is nothing but it is RPM, right? That is revolution per minute. So if I'll convert this revolution per minute into radian per second, that is omega m, so that will become 2 pi by 16 to nm, right? So therefore, after converting this, I'll find the frequency again from here. Your frequency will become, just by substituting this into here, right? So that will become P by 120 nm. Okay. So if your frequency will become P by 120 nm, and nm I can find 120 f by P. So that means if I know the frequency and the pole, number of poles, I can find the speed of the machine, or else if I know the speed of the rotation, I know the pole, number of poles, I can find the frequency of the induced EMF, right? So this is the frequency of the induced EMF, right? Frequency of induced EMF. Okay, so I think your EMF, so your EM, that is nothing but, that is the maximum value of induced EMF will be 5 p omega. So if I'll write it in terms of omega derivative what we have derived earlier, that will become P by 2 5 p omega, right? So sorry, P by 2 5 p omega m, that is in the mechanical speed, right? Now if I'll again convert to nm, in terms of nm, if I'll write, it will become 2 pi p by 120 5 p nm, right? So this is your maximum peak value of the induced EMF. Now if I want to find the average value of induced EMF, that is with the commutator segment, then average value, how we calculate? We calculate like this by integrating 1 by t 0 to t any signal, right, with respect to dt, right? If it is a function of theta, I can write it as theta. So here I can find also in the same way, right? So 1 by, because it is symmetrical, so I can write 1 by pi 0 to pi, and the function is your sine function, so it is Em sine of omega t or sine of theta d theta, right? So just by taking integration, I'll find this, it will become 2 by pi Em, right? So that if we'll just substitute the value of Em, it will become 5 pi omega m. And if I'll substitute the expression of omega m in terms of Nm, so it will become P by 30, 5 pi Nm, right? Okay. So next class we'll continue this force on a conductor, that is motoring action. We studied the generator action, right? How when a coil inside the uniform magnetic field is some force is applied on it, how the induced EMF will be there. All these things we discussed today, and next class we'll see the force on a conductor, how the force on a conductor will be developed when a current carrying coil is inside the uniform magnetic field. Okay, so next class we'll discuss. Okay, so thank you very much. Any doubt till now?